Burge, and Toot, and then walk through the essential algorithms like Hungarian and Gale Shapley.
And no rushed explanations. That's key. We're going to cover everything thoroughly.
Okay, let's get into it. Let's unpack this central foundational concept. The matching itself. It seems, I don't know, deceptively simple on the surface. You're just picking edges, but the constraint is everything.
The constraint is the soul of the definition. It really is.
So what exactly is a matching?
A matching, and we usually denote it with a capital dollar in any graph $10, is a collection of edges that you've chosen. And the one single defining rule is this. No two edges in your set M can share a common vertex.
That's it. That's the law.
That's the law of exclusivity. If a vertex, let's call it dollars, is involved in one partnership within your matching dollars, it's instantly off the market. It's unavailable for any other partnership within that same set dollars.
I think the real power here, especially for someone studying this, comes from how this simple rule then classifies the entire graph. It's all about the status of each vertex relative to the matching you've picked.
Yes, and that's the concept of saturation.
So what are the key statuses we need to memorize?
There are two. First, a vertex favolator is called M-saturated if it's incident with at least one edge in your matching dollar.
Conceptually, it has a partner. It's matched.
It has a partner, exactly. And second, if a vertex dollar is not incident with any edge in dollar, it's M-unsaturated. We often just call it a free vertex.
And that's the one we're interested in when we're trying to improve things, right? The free vertices.
That's the status we focus on. They represent the potential for growth.
And the gold standard, the kind of theoretical ideal, is when we manage to create a situation where, no vertices are left behind.
That is the perfect matching.
Right.
A perfect matching is that ideal scenario where it saturates every single vertex of the graph dollar-dollar. Every vertex has been paired exactly once.
Which means, of course, the graph has to have an even number of vertices to begin with. You can't pair everyone up if you have an odd number of people.
An obvious but critical prerequisite, yes. And achieving this represents, total coverage and maximum utilization of whatever resources the graph represents.
Okay, so moving just beyond the basic definition, we immediately hit a really common conceptual trap for people new to this.
Oh, yes.
The difference between a maximal matching and a maximum matching.
This is absolutely critical, and we need to be crystal clear on this one.
Let's do it.
A maximal matching is one that is locally optimal. It's a matching dollar that you cannot enlarge by just adding any single edge that's currently not in a dollar.
So you can't just stick one more edge in there.
You can't. Any attempt to add a new edge would immediately break the exclusivity rule because that new edge would have to touch a vertex that's already saturated by your matching dollars.
So it's stuck in its current state. It's a local dead end.
Precisely. But, and this is the key, that doesn't mean it's the biggest one possible. It's just a local optimum.
Okay, so then what's a maximum matching?
A maximum matching, on the other hand, is globally optimal. It's a matching that achieves the largest possible size you can get in the entire graph, D dollar.
The biggest one, period.
The biggest one, period. The size of a maximum matching is actually a key property of the graph itself. We often denote it alpha G.
And the relationship between these two terms it's directional, isn't it?
Yes, it's a one-way implication.
Yeah.
Every maximum matching is automatically maximal.
Which makes sense. If it were the biggest possible, you couldn't just add another edge to it.
Right. If you could, it wouldn't have been maximum to begin with.
But the reverse, the fact that a maximal matching might not be maximum. That's the crucial cautionary tale here.
That's the local track.
Let's use the clearest possible example to illustrate this. The path graph seems like a good one.
Perfect. Let's imagine a simple path graph, say 5 vertices in a line, 5 vertices in a line, 5 vertices in a line, 5 V2, V3, V4, V5, V5.
Okay.
Now, what's the maximum matching size here? You can see it's 2 edges. For example, you could pick the edge, VV1, V2 dollar, and the edge, V3, V4 dollar.
And that leaves V5 of dollars all by itself, unsaturated.
Right. The size is 2. That is the largest possible. That's our maximum matching.
Now, how do we get stuck? How do we create a maximal but non-maximum matching here?
We just make a poor choice early on. Suppose instead we choose the single edge in the middle, 1 mmV2.
Okay, so the size is just 1.
The size is 1. Now, is this maximal?
Well, let's see. Can I add the edge V1M, V2? No, because V2 is already taken.
Correct.
Can I add V3, V4 dollars? No, V3 dollars taken. Can I add V4, V4? Yes, I can. Wait.
No, if you add V4, V4, then the matching is V2, V3, V4, V5, which has size 2. That's a different maximal matching. The point is, if your matching is only the single edge, V2, V3, is that matching maximal?
Oh, I see. Yes, it is. I can't add any single edge to the set without breaking the rule. I'm stuck.
You're stuck at size 1. You cannot add any single edge. But we already know that size 2 is achievable, so the matching V2, V3 is maximal, but it is not maximum.
And that distinction is exactly why we need more powerful tools. We can't just greedily add edges and hope for the best.
Exactly. We need something like augmenting paths to check if we're truly optimal.
Which moves us perfectly into the next part, the mechanics of how you actually improve a matching.
Right. This is the central mechanical question of the whole theory. How do we get from a locally stuck maximal matching to a globally optimal maximum one?
And the answer involves looking for specific kinds of paths in the graph.
Yes. Structural exploration using paths.
This is where the complexity starts to ramp up a bit. We're looking for these special paths that basically shout at us, hey, improvement is possible over here.
And we have a name for them. First, we define the M alternating path.
Okay.
This is just a path where the edges strictly alternate. One edge from your current matching dollars, the next one not in dollar, the next one in dollar, and so on.
They're like the structural footprints of the matching itself.
A good way to think of it. Now, the real discovery tool, the one we're hunting for, is a special kind of alternating path.
The M augmenting path.
The M augmenting path.
So what's the specific characteristic? What makes an alternating path an augmenting one?
It all comes down to its endpoints. An M augmenting path is an M alternating path where both of its endpoints are M unsaturated.
They're both free vertices.
Both free. This specific setup is like a geometric signpost saying that your current matching dollars is substandard.
So if we can find a path that starts at a free vertex, ends at a different free vertex, and strictly alternates between matched and unmatched edges all the way along,
Then you have a clear mechanical instruction on how to improve your match.
you flip it.
You flip it. The power of the augmenting path comes from its length. Because it starts and ends at free vertices, the first and last edges must be unmatched. This forces the path to have an odd number of edges.
Right.
So if you have a path, say P dollars, with edges E dollars, E2, E33, and E dollar and 33 are unmatched while T dollars matched, you can perform the flipping operation.
You swap the status of every edge on that path.
Exactly. The matched edges get removed from nadir, and the unmatched edges get added to dollars.
And the result is a new, perfectly valid matching, which we can call $1.
And crucially, the size of this new matching, $1, is exactly $1 plus $1.
Because you had KLR-matched edges and KLR unmatched edges on the path. You swap them, you gain one edge overall.
You've successfully used 2 previously free vertices and increased the total number of pairings by 1. Then the process just restarts. You look for the next augmenting path, and you keep going until you can't find any more.
Okay, so to actually prove that we're at a maximum when we stop, we need a mathematical tool to compare two different matchings. Let's say we have $1 and potentially bigger one, $1.
And that tools is the symmetric difference.
Right. The symmetric difference, which is written $1 delta MM, is what? Exactly.
It's the set of edges that belong to either the dollar or not to both. It's the what's different between them set. It highlights the structural differences.
And when you do this comparison between two matchings, the structure of this difference is surprisingly limited.
It's a beautiful and really fundamental lemma. The components of one Dolnoff states that this symmetric difference can only be made of 2 things.
Okay?
Disjoint paths, where the edges alternate between lattice and dollar, and even cycles where the edges also alternate.
Paths and even cycles. That's it. Why can't we get, say, a vertex with 3 edges coming out of it, or an odd cycle?
The reason is actually quite simple, and it goes right back to the definition of matching. Think about any vertex dollars in this difference graph.
Okay.
Since dollars are matching, dollars can be an endpoint for at most 1 edge in dollar. And since dollars also matching, it can be an endpoint for at most 1 edge in dollar.
So in the difference graph, any vertex can have a degree of at most 2. One from molar, one from
Most 2. And any graph where every single vertex has a degree of 1 or 2 must be a collection of disjoint paths and cycles.
That makes sense.
And because the edges have to alternate between a dollars and dollar, any cycle you form must have an even number of edges to get back to the start.
This structural lemma, this feels like it's setting something up. It's the backbone for one of the biggest theorems in this whole field.
It is. It's the foundation for Burgess' theorem from 1957. It connects that global goal of finding the biggest matching to a very specific local structural condition.
So what does Burgess' theorem state?
It's the definitive test for optimality in any graph, not just bipartite ones, it says. A matching dollar and a graph dollar is maximum if and only if the graph dollar contains no augmenting path.
That's really profound. It turns the problem on its head. Instead of checking every possible combination of edges to find the absolute largest set,
which would be computationally impossible for large graph.
right, instead you just have to run a search algorithm to see if this one specific failure state, an augmenting path, is present or not.
Yes. Let's just walk through the proof sketch. It shows how robust this is. The first direction is the easy one.
If an augmenting path exists, then M is not maximum.
Right. We already showed that if one exists, we can flip it and create a bigger matching dollars. So by definition, dollar couldn't have been maximum. That's the necessary part.
Now for the other direction, the more subtle part. How do we prove that if no augmenting path exists, then $, must be maximum?
This is where we use that symmetric difference lemma. We'll use a proof by contradiction.
Okay.
So let's assume, for contradiction, that $, is not maximum, even though it has no augmenting paths.
So there must be some other matching, let's call it $, that's bigger? So more like...
Exactly. Now we look at the symmetric difference between them. Delta M dollar.
Because $'s bigger, the edges from dollars have to, in some sense, outnumber the edges from a $' in that difference graph.
Precisely. We know the components of that difference graph are just alternating paths and even cycles. On the even cycles, the number of edges from $' and dollar has to be equal.
Right, to keep the alternation going.
So for $' to be larger overall, there must be at least one path component where there are more edges than $' edges.
And for that to happen, such a path must start and end with an edge from $.
Yes. And now think about what that means. If an alternating path starts and ends with edges from $, what can we say about the endpoints of that path?
They're saturated by $ballers, but they can't be saturated by $ball. If they were, the edges attached to them in $' would also be in the symmetric difference.
Correct. The endpoints of that path are M unsaturated. They are free vertices with respect to $.
Wait a minute. A path that alternates between M and M prime edges, and its endpoints are M unsaturated.
That is, by definition, an M augmenting path.
Which contradicts our initial assumption that no such path existed.
Exactly. So our assumption that $' wasn't maximum must be false.
Yeah.
If no augmenting path exists, $' has to be maximum. It's just a beautiful, elegant proof. And it's the cornerstone of how we design algorithms for this.
Okay, that characterization is for any graph at all. But things get even more powerful and beautiful when we restrict ourselves to a special kind of graph, bipartite graphs.
Yes, bipartite graphs simplify the structure dramatically.
This is where we have two distinct sets of vertices, say $6, and edges only run between the sets, never within them. And this is often framed using that classic marriage problem analogy.
It is. And that brings us to Hall's marriage theorem.
Right.
Hall's theorem is fundamental for understanding when a matching can exist in a bipartite graph, Jolly-Blake sense, X cup Y E. Usually, the goal is to find a matching that saturates one entire side, say the set $6.
So ensuring every member of $6 gets a partner from $.
Exactly. And the theorem gives us a clear condition for when this is possible.
The whole condition, what is it?
A matching that saturates all of $6 exists if and only if a certain property holds for every possible subset of $6.
For every sub?
For every single one. For any subset Asali you can pick from 6 eyes of its neighborhood, that's the collective set of partners available tomorrow over $1, which we write as has to be at least as large as the size of SOHORT itself.
So formally, no $' for all subset XX.
That's the condition.
The necessity of this seems pretty intuitive. If you have, say, 5 people in a group, Everdell, and collectively they only have 4 potential partners in their neighborhood number, you're obviously not going to be able to match all 5 of them.
Of course, that's a bottleneck.
The really amazing insight, though, is that this is also sufficient. If this deficit never occurs for any subset, no matter how weird or scattered, then a full matching for $6 is guaranteed to exist.
That sufficiency is the mathematical power of the theorem. It tells you that if the options are collectively large enough for every possible subgroup, then no amount of internal competition or weird overlaps can stop you from finding a complete matching for X. It's a massive guarantee.
It replaces a potentially huge search for a matching with a check on the graph's structure.
Exactly. And this leads directly to an incredibly strong result for a special kind of bipartite graph.
The regular ones.
Regular bipartite graphs.
Where regular means every single vertex has the same degree. Let's call it $. The source says that if a bipartite graph is too regular and $' greater than 0, it must have a perfect matching.
A huge guarantee just from symmetry.
It is, and the proof is such a perfect example of using Hall's logic, but with simple edge counting.
It is. So let's say our graph $$ X cup Y E. First off, because it's bipartite and regular, the number of vertices on each side must be equal. So $60 has to equal that dollar.
Which means a matching that saturates X is automatically a perfect matching.
Right. So all we have to do is prove the Hall condition holds.
Let's walk through that counting argument slowly. This is a key takeaway for anyone studying this.
Okay. Step 1. Pick any arbitrary subset. $6. Any one at all.
Got it.
Step 2. Count the edges leaving symbols. Since every vertex in dollars has degreed Sagae, the total number of edges that have one endpoint in dollars is exactly times the size of summer. So
coming out of the office.
step 3,
Yeah.
all of those edges have to land somewhere in the dollars. Specifically, they have to land in the neighborhood of Sellers, which is Meon. Now, step 4. Look at it from the other side. Let's count the maximum number of edges that could possibly be received by the vertices in LNS. Since the graph is regular, every vertex in LNR also has degree. So the total number of edges incident to LNR is at most times the size in INUS.
At most, at a less.
So step 5, we combine those two facts. The edges leaving Zellers must be accounted for by the edges arriving at NLRs. Therefore, NLR must be less than or equal to KLNR.
And since we said to dollars positive, we can just divide both sides by color,
And you're left with del R.
which is the whole condition.
And since we picked a totally arbitrary subset dollars, this holds for all subsets. So Hall's theorem guarantees a matching that saturates sexes, which in this case is a perfect matching. The symmetry of the graph guarantees the pairing capacity.
Incredible. Okay, let's shift now to the dual problem, the cover.
Yes.
If matching is about maximizing a set of non-intersecting edges, covering is sort of the opposite. It's about minimizing a set of intersecting vertices.
That's a great way to put it. A vertex cover, which we usually call Q dollar, is a set of vertices chosen so that they collectively touch or cover every single edge in the graph.
So if you delete all the vertices in your cover Q, the graph that's left over has no edges at all.
0 edges. And the goal is always to find the minimum vertex cover, the smallest possible set Q dollar that gets the job done. We call it size tau.
It seems pretty clear right away that the size of any matching Noller can never be bigger than the size of any vertex cover, QDOL.
Why is that?
Well, every edge in your matching Noller has to be covered by some vertex in QDOL. And since all the edges in QDOL are disjoint, they don't share any vertices, you need at least one unique vertex from QDOL to cover each one. So it must be less than or equal to QDOL.
That inequality, Molly-Q-dollar, is always true for any graph. But the really profound result, this moment of perfect duality, happens specifically in bipartite graphs.
And this is the Koenig-Egervary theorem.
The Koenig-Egervary theorem.
What does it state?
It says that for any bipartite graph, d dollars, the size of the maximum matching is exactly equal to the size of the minimum vertex cover.
The inequality becomes an equality.
It becomes a perfect equality. We write it as alpha g alpha. The maximum matching size equals the minimum vertex cover size.
This is a classic min-max duality in combinatorics. It connects the best possible outcome of one problem maximum pairing directly to the cost of the optimal solution for its inverse problem, the minimum blocking set.
It's a beautiful relationship, and we can deepen this idea of duality even further by connecting the vertex cover to another concept.
The independent set.
The independent set. This is a collection of vertices, let's call it Zillers,
Yeah.
where no two vertices in the set are adjacent to each other. They're completely disconnected from each other.
And the goal there is usually to find the maximum independent set, alpha G.
And the connection between an independent set and a vertex cover is surprisingly elegant. It's a complement rule.
Right.
A set of vertice dollars is an independent set, if and only if its complement, all the other vertices in the graph, VG set minus SE, is a vertex cover.
Let's just check that logic. If sec of dollars is an independent set, there are no edges running between any vertices inside sec-a-rack.
By definition.
So every single edge in the whole graph must have at least one of its endpoints outside of setter.
Which means every edge is covered by the complement of Zellers.
It's a vertex cover. The logic holds.
And what this means is that maximizing one of these things necessarily minimizes the other. If nen-g is the total number of vertices in your graph, you get this fundamental formula, alpha g plus tau g.
Maximum independent set size plus minimum vertex cover size equals the total number of vertices.
Always.
Okay, we've been focused on vertices. Let's quickly bring in the edge-based version of this, the edge cover.
An edge cover is a set of edges, let's call it dollar, where every vertex in the graph is touched by at least one edge from dollars.
So you're covering vertices with edges instead of edges with vertices.
Exactly. And this is only possible if the graph has no isolated vertices, of course. We're looking for the minimum edge cover size, which we call tau.
And how does this relate to the maximum matching? Is there another formula?
There is a parallel duality formula. Alpha g plus tau g Maximum matching size plus minimum edge cover size also equals the total number of vertices.
And this leads to a really powerful corollary when you put it all together for bipartite graph.
It does. If you have a bipartite graph with no isolated vertices, all these theorems together imply that the size of the maximum independent set, alpha g guy, must be equal to the size of the minimum edge cover.
You've unified the biggest set of disconnected vertices with the smallest set of covering edges. That's amazing.
All because of that special bipartite structure.
And we can see this all play out even in a tiny non-bipartite graph, like the triangle, $3
Right, 3 vertices all connected.
So un9 under the 300s. The maximum matching size alphas is 1 edge. The maximum independent set alpha is 1 vertex. The minimum vertex cover is 2 vertices. And the minimum edge cover is 2 edges.
And the formulas hold $1 plus 2, 333 for both vertex and edge duality.
Okay, so the theorems tell us what the maximum size is and what it's equal to. Now we have to turn to the how.
The algorithms. How do we actually compute these things efficiently?
Right. Let's start with the augmentin path algorithm for bipartite matching. This sounds like it directly uses Burge's theorem and the Koenig-Agervary theorem at the same time.
It does. It's a beautiful piece of algorithmic design. The goal is to find both the maximum matching dollar and the minimum vertex covered $2 in one process.
And it's basically a graph traversal, like a breadth-first search or depth-first search.
Yes, but a special kind. It systematically explores M alternating paths, but it only starts them from the M unsaturated vertices in X, which we can call the set $2.
Let's focus on the sets we're tracking during the search. There's an A, B, and $, and a $.
Right. $7 is the set of all vertices and savas that we can reach from our starting unsaturated set. $2, but only by following M alternating paths.
Okay.
And $7 is the set of vertices in dollars that are part of this alternating path structure.
So how does an iteration of the algorithm work?
We start the search from $. If our search ever lands on an unsaturated vertex over in dollars, we've found it.
An augmenting path.
An augmenting path. We flip the matching along that path, which makes our matching $1 bigger, and then we restart the whole search with our new, slightly smaller set of unsaturated vertices, $2.
And what if the search finishes without finding one?
If the traversal completes and we never found a free vertex in Y, we stop. By Burge's theorem, our current matching dollar must be maximal.
Now here is the crucial conceptual leap that I think can be confusing. The algorithm stops, and suddenly the final state of those sets, $7 and $, magically defines the minimum vertex covered dollars.
It's not magic, it's structure. The minimum vertex cover Q is constructed like this. Q cove T cup, X set minus S. So it's all the reachable vertices in Y, plus all the unreachable vertices in X.
Okay, let's prove it's a vertex cover. Every edge in the graph has to be touched by a vertex in Q.
Right. Think about any edge, 6Y. There are a few possibilities. Case 1, $6 is in 6 off through a Q by dollar.
Well, in that case, $6 is in our cover Q by definition, so that edge is covered. Easy.
Good. Case 2, $6 in dollars. Now what about its neighbor? If $6 is in $2, then $1 is in a cover Q, so that edge is also covered.
Okay, so the only tricky case is what if it's $6 and its neighbor B is not in dollars?
And we argue that if the algorithm is terminated, no such edge can exist.
Why not?
Think about it. If we have an edge from a reachable vertex, 6x into 2, to a vertex dollar that is not in dollar, what does that tell us about people? Well, you must be unsaturated. Because if you were saturated, it would have a matched partner, say dollars. And since $6 and 7, our alternating path search would have explored the edge to dollars, and then the matched edge from J to time, which would have put dollars into dollars and dollars, and by definition put J into dollars. The only reason J dollars isn't in dollars is if it has no matched partner to continue the path.
So tie is a free vertex.
And if Yellers is a free vertex connected to 6 eyes, we've just described an M augmenting path.
But we assumed the algorithm terminated because it couldn't find one.
It's a contradiction. So that type of edge cannot exist. Therefore, our set Q dollars covers every single edge in the graph.
And it can be mathematically proven that the size of this specific cover, Q dollars, is exactly equal to the size of the maximum matching dollar we found.
Satisfying the Koenig-Agervary theorem perfectly, the algorithm gives you both optimal solutions at once.
Okay, let's move on to weighted graphs. This isn't just about maximizing the number of pairs, it's about maximizing their value.
Yes, this is the classic assignment problem. You're given a complete bipartite graph, getting a WAS, with weights on every single edge, and your job is to find a perfect matching that maximizes the total weight.
And this introduces this really interesting idea of duality in terms of costs and labels.
It does. To solve this maximization problem, we look at its dual, which is a minimization problem. We assign numerical labels to all the vertices. Let's say a vector $4 for the vertices and $6 and a vector $5 for the vertices and dollars.
And these labels have a rule they have to follow.
They do. They have to satisfy a feasibility constraint. For any edge between vertex Eilers and vertex Geller, the sum of their labels, we plus v-Dagger, has to be greater than or equal to the weight of that edge.
So the labels have to cover the weights.
That's why we call it a weighted cover.
Yeah.
And the cost of this set of labels is just the sum of all the labels. V, sum of u plus moco vin g.
Okay, and the weighted duality lemma ties this all together.
It does. It guarantees that the cost of any feasible set of labels will always be an upper bound on the weight of any perfect matching. So Tu is always greater than or equal to.
And optimality, then, is when you find a matching in a set of labels where that bound is tight, where they're equal.
Exactly. You've found the optimal solution when you find a perfect matching dollars in a set of labels where for every single edge that's in your matching, the equality holds. 1 plus VEIU.
So the total cost of the labels equals the total weight of the matching. Primal and dual problem solved.
And that structural requirement that the optimal matching has to live entirely within the set of edges where the labels and weights are equal is the key insight behind the algorithm.
The Hungarian algorithm.
Right. This is the equality subgraph DUV. The Hungarian algorithm's genius is that it starts with some feasible labels. It tries to find a perfect matching just inside that equality subgraph.
And if it fails,
It systematically and cleverly adjusts the labels to introduce new helpful edges into the equality subgraph while always making sure the total cost of the labels goes down.
let's talk about that label adjustment step. That's the core of it. So we've found a maximum matching in our current equality subgraph, but it's not perfect yet. We're stuck.
We are, so we run our augmenting path search again, but only on the equality edges. We find our reachable sets, $6 and $16. Since we failed, we know there's no augmenting path within the current equality subgraph.
So the solution is to create a new equality edge where the search got stuck, between some vertex in our reachable set dollars and some vertex that's not in the reachable set $2.
Precisely. And to do that, we need to calculate the slack. We call it alpha.
What is that?
The slack, alpha, is the minimum amount by which any edge between $6 and the unreachable part of a set minus t fails to be an equality edge. Formally, it's alpha min plus vj ig for all dollars and dollars and noten.
And since we're stuck, this alpha has to be positive.
It has to be. Now, here's the adjustment. We decrease all the we labels for vertices in Lada by alpha, and we increase all the v-Jella labels for vertices in Tala by alpha.
Okay, hold on. Why that specific manipulation? What does that do?
It achieves three critical things at once. First, for the specific edge that defined alpha, this adjustment makes it into a new equality edge.
It adds an edge to our search graph.
Exactly. Second, it maintains feasibility for all the other edges. The labels still cover the weights everywhere else. And third, and this is crucial, it strictly decreases the total cost of our label set, $5 dollars.
So it's guaranteed to make progress towards the optimal solution.
Every single step gets you closer. It's designed to preserve the matched equalities we already have, while systematically searching for a path to completion by reducing the slack across that search boundary.
And it's incredibly efficient for what it does, Thor running time.
Yes. Now, we need to make a pretty big conceptual pivot. We've talked about maximizing size and maximizing weight, but there's another goal.
Maximizing satisfaction, stability.
Exactly. The stable matchings problem. This is where preferences rule. Think matching medical residents to hospitals or students to schools.
This is a totally different ballgame, because we're not just looking for any perfect matching. We want one that is resistant to being broken up by people deciding they'd rather be with someone else.
And that's the definition of stability. A perfect matching is stable if there is no blocking pair.
A blocking pair.
A blocking pair, sex-wise, is a man and woman who are not matched to each other, but who both prefer each other over their current partners.
So they have an incentive to ditch their current partners and form a new pair.
Right. If a blocking pair exists, the matching is unstable. They will block it.
And the Gale-Shapley algorithm from 1962 gives us a way to always find a stable matching. How does this proposal system work?
It's an iterative process that's structured to give an advantage to one side, usually the proposers. Let's say the men are set X.
Okay.
Everyone starts free. In each round, any man in X who is still free proposes to the highest-ranked woman on his preference list that he hasn't proposed to yet.
And the women.
Each woman looks at all the proposals she's received. If she's free, she'll provisionally accept the best one. If she's already holding a proposal, she'll compare the new one to her current one and keep the one she prefers, rejecting the other.
And rejected suitors just move on to the next person on their list?
Crucially, once a woman rejects a man, that's it. He can never propose to her again.
This simple process, it's guaranteed to end in a stable matching. Why? Why is it stable?
It's because of how the proposals and rejections work. Let's say we have a final matching, and we imagine there's a blocking pair, high X. This would mean 6 prefers dollar to his final partner, and we prefers 6 to her final partner.
Right.
But did 6 ballers ever propose to Ya during the algorithm? If he didn't, it must mean he got matched with someone he prefers even more than Ya, so he wouldn't want to block.
Okay, so he must have proposed to her at some point.
Right. And if he proposed to her, she must have rejected him at some point. Why would she reject him? Only because she got an even better proposal from someone she liked more. And since women only trade up, her final partner must be someone she prefers to $6.
So she wouldn't want to block either.
The existence of a blocking pair is a logical impossibility. The algorithm prevents it by its very structure. It always terminates, and it's fast dollar.
Okay, we have covered bipartite graphs and their really elegant solutions in a lot of detail. Now we have to face the music. General graphs. Non-bipartite graphs where everything gets significantly harder.
It does. The structural analysis is much more complex.
Our challenge here is to find a condition for a perfect matching that works for any graph, even ones with odd cycles.
And that brings us to Toots' one-factor theorem.
First, a one-factor is just another name for a perfect matching, right?
Yes, it's a spanning subgraph where every vertex has a degree of exactly 1. Same thing.
And Toots' theorem introduces this idea of a structural deficit, and it uses the concept of the odd component. What is an odd component?
An odd component is a connected piece of a graph that has an odd number of vertices. And the key insight is that if you have a chunk of a graph with an odd number of vertices, it's impossible to have a perfect matching just using the edges inside that chunk.
Someone has to be left over.
At least one vertex must be left unsaturated internally.
And that structural necessity, that's the key to the whole theorem.
It is. Toots' one-factor theorem from 1947 gives us the condition. It says a general graph, D-Allers, has a perfect matching if and only if, for every possible subset of vertices that you can pick.
For every subset.
For every single one. You take the graph, you delete the vertices and dealers, and you look at what's left over, which is $$ set minus SME. You then count the number of odd components of what's left. Let's call that OG set minus S.
Okay.
The condition is that this number of odd components must be less than or equal to the size of the set dollars you deleted. So OG set minus S.
Let's unpack the why behind that. So let's assume the graph does have a perfect matching dollar. We delete a set of vertices dollars. What happens?
We'll look at one of those odd components, solars, in the graph that's left over. As we said, it has an odd number of vertices. So internally, at least one vertex in Sol Burler has to be left unmatched by the edges that are also in Salers.
But if nullars is a perfect matching for the whole graph, that leftover vertex can't actually be leftover. It has to be matched to something.
And the only place it can be matched to is a vertex back in the set dollars that we deleted.
So every single one of those odd components has to send at least one matching edge out to connect to the set Sol dollars.
At least one. And those edges have to go to distinct vertices in Solars because it's a matching. So the number of vertices you need in Zoller to absorb these connections must be at least as large as the number of odd components you've created.
So if you ever find a set dollars where you create more odd components than there are vertices and sellers to handle them,
You've found a Toots set. It's a structural bottleneck, and it's an ironclad proof that no perfect matching can possibly exist. And Toots' genius was proving that this condition is not just necessary, but also sufficient. It completely characterizes the existence of perfect matchings in all graphs.
and this insight isn't just a simple yes-no for existence. It can actually quantify the size of the biggest possible matching.
Yes, it generalizes the idea. The size of the largest possible matching is determined by the worst bottleneck you can find in the graph. The formula is, the maximum number of saturated vertices is equal to the minimum of do G, OG set minus S us, taken over all possible subsets dilly dollars.
That looks a little intimidating. How should we think about that conceptually?
The part in the parenthesis, do G set minus S, that's the structural deficit created by the set zilly dollars. It's the minimum number of vertices that must be left unmatched because of that bottleneck.
So you find the worst deficit in the whole graph, and you subtract that from the total number of vertices.
And that tells you the maximum number of vertices that you can possibly match. It's another beautiful min-max statement, like Koenig-Egger vary, but for the general case.
And from this, we get some strong corollaries for regular graphs.
We do. For instance, Any three regular graph that doesn't have a cut edge or bridge is guaranteed to have a perfect matching. The high connectivity is enough to prevent a tut set from forming.
And for even degree regular graphs,
Any regular graph of even degree must have a two-factor,
a two-factor, that's a spanning subgraph where every vertex has a degree of exactly 2.
which means the entire graph can be decomposed into a collection of disjoint cycles that cover every vertex.
Huh.
Another fundamental result showing how these degree requirements shape the topology of what's possible.
Okay, this brings us to our final stop on this theoretical journey, the ultimate generalization of all of this.
The factor.
The Fev factor. This unifies all these different degree constraints into a single framework.
It does. And Phi factor lets you assign a custom degree requirement to every single vertex independently. You have a function, $5, that maps each vertex to a number, and you're looking for a subgraph where the degree of every vertex dollars is exactly the number of the veri you assigned it.
So $5 is like a custom blueprint for the subgraph you want to build.
It's exactly that. And you can see how all our previous concepts are just special cases of this.
If you set $5 for all vertices,
You get a one factor, a perfect matching.
if you set $5 to P22 for all vertices,
You get a two factor, a cycle cover.
if $5 is just a constant dollar, you're looking for a k-regular spanning subgraph.
But $5 can be totally non-uniform. You could say, I want vertex 1 to have degree 1, vertex 2 to have degree 3, and vertex 3 to have degree 0. The theory of Fev factors helps determine if such a subgraph can exist.
It's an incredible demonstration of how graph theory progresses. We start with a simple constraint. 2 edges can't share a vertex, and we build all the way up to this highly specific, customizable degree blueprint for a subgraph that covers the entire graph.
It's the framework that lets combinatorial optimization move beyond just simple pairing into things like complex routing, resource allocation, and connectivity problems. As the source material puts it so poetically, edges court in pairs, with elegance precise, covers cloak them modestly, insets concise. Matchings meet their maxima, cycles softly spin, toot whispers, perfection lies within.
A great way to summarize it.
So to recap, we've really dug into that duality principle, the idea that the maximum size of a matching is deeply intrinsically linked to the minimum size of a cover.
Right. We started with the fundamental rules, exclusivity, and saturation, and then we identified the augmenting path and Burge's theorem as the ultimate structural test for whether a matching is optimal in any graph.
The duality theorems are probably the most critical takeaway for you as a learner to get clear. The Hall condition for when a matching even exists in bipartite graphs.
And that perfect equality between the maximum matching and the minimum vertex cover from Koenig-Egervary, those ideas are the bedrock of so much of network flow and optimization theory.
And we showed how to turn that theory into practice. We detailed the